Welcome, everyone. Hopefully you'll have a good Thanksgiving, and if you're looking at this in future semesters, well, hopefully you had a good Thanksgiving. We're going to go through a few things today that are of pretty high importance, so I want to try and get through some of the basics of how to use and operate this particular package. So this is a very nice little software add-in to MATLAB that I want you guys to really pay attention to how it's being used and what we're going to be using it for, why we're doing some of these things. One of the first things that you want to recognize is you want to be in control of what your directory is in MATLAB. Again, this is fundamental to all the things you're doing. You need to not be in user, app data, temporary roaming folders, etc. You really want to be in your documents, specifically under your MATLAB file. So you always want to control exactly where stuff is going. Then if you organize stuff in folders like I have here, a lot of them start out grayed out. You always need to right click, add to path, selected folders and subfolders. Because if you don't do that, you won't have access to the things that are in that, even if you have them open up here. So again, if you have not been awake during class or whatever else has been the case, command window, really, really super important. But even more important is the window that's going to open up when we look at these M files. So SFBM is what we're using. So this is about beam mechanics and what actually happens with static forces applied, different kinds of supports and things like that. This is a really, really useful and helpful example of a package. One of the first things that I want you to look at is this thing called README. It's almost like it's giving you instructions for good reason, so something that you want to pay attention to. There's a reason that these exist in files. We're going to open up this first, and we're going to take a look through it and see what's happening. So this stands for shear force and bending moment is what this stands for. This code is really well done. It's a very nicely done package. What it helps with is development of free body diagrams, things that you guys will come to need much, much more later in your later semesters, things that you'll come back to all the time. There's a kind of some background code done in a couple different aspects of different programming languages and things here. That's not the important part. There's some documentation things that are also developed pretty well, just things that you want to be generally or broadly aware of. Couple things is you have a couple different arguments that go into this process, and so the first one is something about the name, and we're going to look at this and see examples of this in this process. I just want you guys to actually see exactly what's going into this. So this will be sort of part tutorial and then part of setting you off to do a whole range of testing on your own. So we'll talk about how to make changes and what those look like in the end figures. Try and make sure that you guys are easily able to see all of the things that are going on. So the second argument is what type. So is it a cantilever? Is it a beam on the floor? Is it a simply supported beam? All of those things have distinct meanings, and the point is not to understand all of beam mechanics and bending moments and all of those things. Again, the whole purpose of all of this is to show you guys how to use tools in order to make things happen. So we have to use tools in engineering all the time to understand how to do this. Again and again and again, you guys have had to work on, in this whole semester, building the tool, taking the measurement, and then doing the graphing of the data to understand what the relationship is between a set or a range of numbers. This is the process that we use as engineers to understand what's happening in the world. And a lot of other disciplines use that same kind of process, but engineers do it as just a core part of literally everything we do. So we want to keep this in mind as we go to do this. So simply supported beams are most of the early kinds of cases. Cantilever beams are where you have one end supported and the other end hanging in free space. Lots of different applications for those. And there's also possibilities for a beam that's lying on the floor without any particular point support. And that's where, depending on which one we're choosing, we use these different keywords, and that's written into the code, so the code will understand what those abbreviations are. But you have to pay attention to the title case here. So capital C, capital F. Don't type lowercase c, lowercase f. You will not get it to run correctly. You'll just get the red love letters down below in the command window. So pay attention to title case in programming in MATLAB in general. All of these parameters have to be titled specifically. This is why the README for a package like this is so important. So this is the thing you come back to consult. So an example argument, a downward point load of 5 newtons, 4 meters from one end of the beam. The argument, the thing that you're passing into the function or asking the function to do something with, the information that you're asking it to act on, is capital C, capital F in single quotes, not in double quotes, single quotes, and it has to be in the curly braces, not parentheses, not the square braces. It has to be in curly braces, not in the square brackets. So everything has to be this way because of the syntax, because reasons. So C, F, both capital, -5, downward, 5 newtons in magnitude, location 4 meters. So everything, all of the arguments are assuming metric. If you put in information in other units, you will just be incorrect. This will create some significant issues for you. If the force is acting upward, then the value of this changes, right? So -5 to +5. Clockwise moment of magnitude, 10 newtons per meter, or Newton meters rather. This moment has the same units as a torque. It's very similar kind of idea. The location, 14 meters. So you would say moment, then you would say, because this is clockwise, -10. So -10, and then 14 meters. So they're telling you about things like units, and that way you can understand what's happening in the code. If you want to go the opposite way, go anti-clockwise, that would be positive. So that's a convention thing as to why they do that. You'll learn more about the specifics of some of those conventions later on for the MEs. The double E's may not spend as much time on it, and the BMEs may not either. So couple more kind of quick things is understanding how to do a pair of supports, for instance. So a uniform force, so 5 newtons per meter from points 2 to 10 meters. The way that syntax looks is like this. So DF, distributed force, again, all capitals. So 5 newtons per meter, distributed force at 2 to 10 meters. So that whole distance has a 5 Newton per meter force distributed across it. So same kind of deal. This would be at this would be a couple of loads. So linear profile is described this way. And depending on whether or not it's uniform, that's what he's getting at here. So he's getting at, the author is getting at from, again, 2 to 10. We have a uniform. And then this one, because there's 3 possible dimensions for the beam calculation, each of the 3 of these is going to give you no meaningful difference. But if the forces are different, then you'll get a polynomial. So this is just trying to describe in 1, 2, and 3 dimensions what the differences are. So 2, 8, and 10 is going to give you the same values there. So the polyfit is probably the function that they're using deep inside this code. We'll see some examples where we run some things. So they'll give you a default and this is the main master function. So we give it that title. So you're going to want to title these specifically, and it doesn't matter exactly what you title them, but they need to be something that tells you what's happening. So they give an example problem here, and this is something that you see as a starting point. So we copied this information over for the starting point of the assignment in order for you guys to see the example code. So problem 200 is a beam of length 20 meters. It has supports at 5 and 20 meters. So we have our 20 meter length, and 5 and 20 is our distribution for this. We have the first step of this. We have an example of, again, our point load. So CF, this is a force or a point load. We have a bending moment, and we have a distributed load example, all in this same function. So in the curly braces, what we're doing is we're calling in, we have a point load of 2 newtons at 0. So at the end of this beam, we have 2 Newton load. We have a bending moment. So the bending moment is 10 Newton meters. Because this is positive, it's anti-clockwise. And that's at 0.8 meters. We have another one, another moment that is clockwise at 12 meters. So same magnitude at 12 meters going the opposite direction. Then we have a distributed force example here. And so what we're doing in this function call is we're giving just a series of all of these different loadings, and this is the stuff that we're primarily going to be changing until we change some of the lengths. So what we're trying to do is see what these mean, and I'll help you a little bit interpret what the graphs are going to look like at the other end from the function, so we'll talk about that a little bit. So we have a point load, we have a moment, we have a distributed force. Again, this one is 5 newtons from 5 newtons per meter from 1 to 3 meters. We have our second moment. We have a second distributed force. So this one is in the opposite direction. So -4 from 4 to 17 meters. So we have all these different combination of things. And notice our syntax making sure all of the curly braces, brackets, everything, parentheses, all of that closes in order to keep from getting errors. So this is the thing that you're going to copy over. Now we'll look and see what is actually taking place, because we're going to open up and look at this sfbm.m file, but I also have an example script here that I'm going to start with just to show you guys what we're actually doing, because these M files you don't need exactly, but it's going to call on each of these to do some different things for some of these examples. So we'll take a look at this. So the solution is going to generate a free body diagram with a legend. A shear force and a bending moment diagram are also going to be generated, and that's what we're going to take a look at. So if there is a shear force, if there is bending moment, it will generate those graphs automatically. So let's take a quick look. I'm going to go ahead and open up testing because this is an example that I was using by copying over that by copying over this one, the SFBM file. So if we open this one, we'll see what the actual function is. Looks real scary and terrifying. Don't make any changes to this or you'll regret your life decisions. So just know that it's here. You're going to have number of variables going in, number of information coming out. So they have a few examples. Yeah, this is one of their example files. Actually, I think that comes in the zip folder. Let me confirm that real quick to minimize some of the extra confusion. Testing, yes, okay. This is one of the ones that I was running earlier, but it's included in the zip file with a lot of very clear commentary as to what's actually happening. So it's reasonable to go ahead and run from this testing because it carries over a lot of that commentary. You can see back again examples of what those look like. Because we're going to be changing those numbers and looking at a bunch of different cases, then comparing how the diagrams change from one set of conditions to the next. And that will help to kind of clarify what's actually happening. So problem 1 is a good example. What I'm going to recommend you do at first is you're going to click and drag all down here. You're going to right click and you're going to comment this out so that when you run it, you're going to just isolate this section for problem 1. And this is where we want you guys to be focused. Because again, this is not about mastering all the fundamentals of beam mechanics, but teaching you a tool that will allow you to do some analysis and study the graphs and compare the data for different sets of conditions. So first one we do is, this is already the default. Let's check against your criteria. So you have to have 20 meters. You have to have supports at 5 and 20. So length of 20, supports at 5 and 20, okay, check. We need to have one kind of force, that's a point force of 2 newtons at 0.0. So yep, 2 newtons, downward direction, 0.0, good. First torque is a moment that we're applying, so 10 and 8. Then we have a second torque, so we're assigning this just to a variable name, keep things a little simple and clean when we go to do the function call. There's a whole bunch of reasons why you want to do that. It's really good practice, and this is why I recommend doing this, and we're not doing stuff in the command window for this particular project. It makes life a lot simpler that way. So we also need distributed loads, one of which is the 5 Newton meters from 1 to 3 meters. So this one, distributed 5 Newton meters, 1 to 3 meters. Second distributed load that is -4, and it's from 14 to 17, so that part checks out. So D2 and D1, each of these distributed loads, each of these torques that are applied. So that second torque that we need is that clockwise 10 Newton meters at 0.12. So this is the example that we used, but we have to make sure that these numbers are correct. So you might have a mean instructor who came in and changed some of these, I don't know. So once we've got this set up, all the rest of this that's commented out with the percent signs won't run. We're only going to be running this block of code. So let's take a look at what we get for graphs. All right, so what this does is a very nice job of representing the information that's contained. So we'll walk through it quickly, kind of from one end to the other. So there's equations given as far as the bending moment that's being applied, how it's being applied, what the equation looks like for the shear force versus the bending moment, what the coefficients are. So it does a lot of work solving some of the difficult things for you, which makes things really nice. So let's see what we can spot. So here's our 2 Newton at the 0.0. Here's our one of our distributed loads here, so 5 kilonewtons per meter. So that's that. I'll want to double check units and make sure that it's behaving correctly the way that it should be. Their default display might be kilonewtons, even though it's supposed to actually read in newtons here. So that may be an update that we need to make in the code. That may be buried deeper in some of the latex code that they did. I'll have to take a look. So we have our moment. So that one is again 10 kilonewtons, then 10 kilonewtons in the opposite direction. So we have kind of counter-rotating forces here. separated by a couple of meters. So these are our bending moments, and that's what's represented by these. A whole bunch of reasons why those are particularly helpful, and we'll get into more of the mechanics of that. So this will help to get more of the pieces and parts that we need. So what we're going to do is also check to see that our second distributed force is applied here. So it's kind of broken up into these different ranges where we have different kinds of loading being applied across the entire 20 meters of length. So and again, this is reading in kilonewtons per meter, so that might be a defect in their LaTeX script. All right, so we have also our shear force, V, our shear force diagram, and our bending moment diagram. So this tells us a number of different things about how this beam is going to be behaving, and we'll look at some of the changes in this, because what we're trying to get out of this is we're trying to change. You'll have a series of instructions that are going to look at individual variables and make changes to each of these. The idea is you're going to change the support lengths for these same exact loadings, and then see how things change in these diagrams and in the free body diagram. And that way you're going to see what happens when you vary where the beam is supported. So maybe you support it at 8 and 12 meters instead of 0 and 20. Or I guess this one instead of 5 and 20, sorry. Because 5, these dashed lines specifically, are where our supports are. So the total loading at each support also gets calculated for you. So very, very handy process overall in order to get the things that are needed to understand what's going on. So our shear force V, this is the thing that's trying to sort of tear the beam apart. And what that's going to do is that's going to tell us where that is the highest and where it is the lowest. So it's at a peak right here just before the support, and then it drops significantly. So the total shear force, and again, I think just because of the way the scaling is set up, if these were actually supposed to be in newtons, either they've got the wrong display or it's in the LaTeX code. So if that gets figured out, I'll post in the comments what that actually is. So it's assuming I get time. So what we've got here is we've got our kind of almost average across the section of the beam that's in torsion here. So this is why it's important to have these up sort of side by side to understand what's going on. So at 14 is where the load changes, and we pick up that supported load all the way to 17. So we have a lot more shear happening. And so the highest overall order of magnitude for the shear is down below. And you can kind of click on a couple points anywhere in the graph to figure out what values you're at. So a swing from plus 8 kilonewtons down to just shy of 10 kilonewtons. So there's about an 18 kilonewton span there from one side to the other. So again, it goes back to 0 over here where this particular end is supported. So very interesting kind of geometry. There's a number of small things that are happening. You'll learn some of the nuances, like why this dip is there, for instance. You'll learn some of those nuances in some of the later courses where you learn about statics. But it's just important to understand that as you go along the length of the beam, which is what this axis is, as you go along the length of the beam, this will give you a sense of how far or what the level of change is in this case, the torque as well as the shear. So this is going up and up and up and up until here about at 8, well, what's happening at 8? This is right where you're applying the torque. So you would expect it to be very high at that point. You'd expect that to be a local peak because that's a high stress concentration point. Then you come down and you go the opposite direction at 12. So the overall magnitude is still rising, and your average is going to be somewhere probably around that 29.2. There's mathematical reasons for that. We're not going to get into that now. Then you have that distributed load again, changing how this behaves from 14 to 17. And then as it goes to the other end where there's a support, the bending moment goes down. So the bending moment itself is highest in between those, and you can kind of you can kind of zoom in and out using the scroll wheel. So let's zoom in a little bit, see if we can grab this top point. It's a little tricky. There we go. Close enough. So around 41 is our total, 41 kilonewton meters. Again, should actually technically be Newton meters. So this gives us our overall peak, which you can tell is significantly higher than any of our single inputs because of how these work together in combination to give us our highest overall point. And it happens just a little bit into that distributed loading that we have this this really high value. So right about here is physically in the beam. So now what you're going to do is you're going to say, okay, all right, we've got screenshots of this as our baseline. Now we're going to come in and say, okay, instead, let's change the support lengths to, we said we were going to do 8 and 12. So 8 and 12. You may want to leave the comment here just to know what kind of the original values were, and just note that you changed it to 8 and 12. So this gives you a kind of a breadcrumb trail to come back to the original function so that you don't have to save multiple versions and cause yourself extra headache. So this alone, when we run this, it's going to give us a little different kind of example. So now we have very different shapes, and we have much, much higher overall shear and a much larger span. So by changing where the beam is supported, now maybe depending on what material it is, this shear might be too high. We might not be able to support it. So it turns out if you hold something in very close, like in, I think it was Karate Kid, where he's holding on to the bar and you have buckets full of water or rocks at either end, if you're trying to balance by a very close grip, something like a barbell in the gym, something like that, and you have big heavy weights on either end, it turns out that's a very high shear force that can create right at the point in between those supports. So it can cause a lot of anxiety if something starts to measure, something starts to bend. So this bending moment is very, very high right where the hands are, and you feel that when you're struggling to try and keep it balanced, right? This is why it's such a good balance exercise, is because it puts such a high overall stress on the two support points. So great for working small muscles, not so great for the health and life of your beam if it's not made of the correct material designed to handle this. So we have a very different kind of load, and what I want you guys to talk about in the discussions is, okay, we changed the support points. Then what happened is the graphs changed. I don't want you to just say that they changed. Talk about things like the magnitude. So why is it so much higher now, or in this case lower, to have the shear force at these 2 points different right? Think about what's actually happening. You're now supporting it at the point where you're torquing the loads, and things like equations change for this. So there's a whole bunch of other factors that happen here. And you want to pay attention to things like how, especially in the sections, there's some conserved themes that you will see, and you want to talk about this. There are some conserved themes in terms of how the shear has a ramped value here with respect to the distance. So again, thinking in terms of the derivatives that you've looked at, and what's actually happening physically with the beam. There's a range, and there's a change in the behavior of the beam. Back down here at the end, you want to think about, well, this is now 0 for the shear at the very end. Well, why is that? Why is it 0 shear out here at the end? So these values, by comparison, have to be much, much stronger supports in order to be inboard. So you want to keep that in mind as you're going through each of these steps and kind of explaining what's happening with the diagram, how it changes so drastically between the two supports as far as the total bending moments. One's going one way, one's going the other way. And because you're supporting at the points of the bending moments, that's part of why you have the peak values at those two places. So you're going to change to a couple different sets. You want to try and do about 3 changes or 3 different sets of lengths. You don't want to use the same ones that I'm using. You just want to make sure that you're looking at 3 different sets of positions and see, okay, maybe if I support it at 20 and then at 18, what happens then? How strong do they have to be? All of those sorts of things. And you want to talk about what's different about the graph and why. There are some conserved features like this derivative that you see, the shear with respect to x. So there's a positive shear slope to this. There's a negative slope over here. So you want to be just thinking about what that has to do with things with the direction of the loading and all of those sorts of things. Then you want to make some additional changes. So you want to change at least one different set of support lengths. You want to change, I think the write-up also asks you for 3 different kinds of point loads. So the first point load that you do, the first point load here is -2. So instead, you want to go then, change it back and change again, one variable at a time. This is why you need your breadcrumbs. So changing one variable at a time, being a good little scientist, and you're going to change to a different kind of loading. So this one, maybe we do -15, and we do it at 0 and see what happens to those at that point. So changing one variable at a time. So this overall looks similar, but now what we can see is, it's very interesting. We now have, again, very, very different graphs. So we have a negative moment on this side below 5. We have a very positive slope to this moment versus position graph. So this part remains sort of similar in shape. The relationship changes, but this first portion of the graph is very, very different, all because of how this loading changes. So if we move that position along, that's another thing that you can do, is not only vary the magnitude, but vary the position. What happens if you put the point load dead center? What does that do? Well, let's take a look. So if you put the point load at the dead center and you say at 10, what do we get? So now we see this part has a very, 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 very small overall load, but our bending moments now are very high in comparison, so significantly higher than they were for the other cases. So our overall shear has still a pretty large span, but now we have one support that really isn't bearing a whole lot of the weight, and we have the other support that's bearing the majority of the forces, the sum total of the forces between the bending moments and everything else. So by changing and optimizing this, what we're trying to get you guys to understand, thinking in the big picture sense, is we get a sense of what's actually going to be included in the loading of beams. And what we're trying to do is we're trying to get you to understand that by changing the position of where the load is applied, by changing the position of where we support a beam, for the same set of conditions, any one of these variables can change things like how strong the material is that it needs to be made out of and how much it actually has to weigh. And then how much do these supports have to carry? So your design decisions change based on the kind of information that you get here. You could even add in a second point load at the end and see what happens at that point and see what changes. Does it only change at this support, or does it change both of them, right? So you could have one that's going upward or something at this end. So real quick, the way to be able to do that would be to add another one. And you would say a force 2 is equal to, so we're assigning a new variable, and we're going to give it the same kind of curly brace interaction here. You're also going to suppress the output by ending with the semicolon, because don't ask questions you don't want the answer to. So if we did this, just to keep things a little bit faster, and we had a plus 15 at 0. Let's see what this does. So when we go to run this, we're going to need to include an F1, F2 to include our new variable here. We run this, we're going to get a very different kind of graph yet again. So similar in the overall shape and geometry, more or less for the shear force diagram, larger values. It's mostly what we get out of this. But now we have a change in the direction of the loading of our support. So this time, now the support actually has to pull down at this point with a very strong force larger than this. And this one has even more weight to support, even though this one now has to sort of be holding the whole apparatus down. So by changing these directions, we change a lot of things, and you see the equations vary wildly, but again, they're comprehensible in terms of their piecewise inclusion. So you want to be talking about what's different in the graph and why, and in particular, what's changing as your support conditions when you make the changes to these variables. So you're going to walk through, you're going to change distributed loads, you're going to change the point loads, you're going to change all of these, and you want to understand where is the beam kind of under the most total stress. And now think for a moment, in the sections that you've gotten into, you've been doing derivatives, and now you're starting to kind of get into integration. What do you think is the overall stress that the beam is under? And without getting too far into some of the principles that you'll learn about later, you want to just think about that in terms of the total area under the curve. Where is there more bending moment under the total, or where is there more total bending moment area? Where is there more total area for the shear? And that will give you some additional information as to what the differences are between the total stress that's applied to the beam. So we're not going to get into the particulars of stress and strain. Again, we're trying to just keep a very high level of conception about this, but trying to explain what we see in the differences of the graphs and why these are so important, even though on the face of it, this diagram kind of looks the same as the other 3 or 4 versions. But it's very, very different, particularly because of what's happening at these supports. So those are the things that we want you to be considering. So, good luck. Hopefully you'll keep very good notes and keep track of what things you change so that you can change one thing successively at a time. Then by the time you get to the end, you can explain what the changes are and why that made the kind of change that it did in the graph, because you really, really want to dig into the detail, and there's a lot to talk about. So a lot of good examples of things that you can change and adjust. You'll probably also want to update this in order to update the graphs. So each time you do another one, you probably want to do version 2, 3, 4, etc., so that you can much more easily keep track of screenshots and not get confused on which one was which. So good luck, and we'll see you when you turn all of them in and hopefully come back from Thanksgiving, unless this is next semester, in which case, well, hope Thanksgiving was a good one. Catch you guys later.